Let's do some examples. And these are just going to be a couple simple examples to get us started. So we'll do some more detailed examples as we go through the course. For this one, let's start out reading the problem. So the specific volume of 5 kilograms of water vapor at pressure of 1.5 megapascal and a temperature of 440 degrees Celsius is 0.216 cubic meters per kilogram. What we want to do is find volume, and we want to find the amount of vapor present in moles, and then we want to find the number of molecules. All right, now I picked this problem out because it's got a couple of different things we haven't talked about yet, namely moles and finding molecules. So I wanted to make sure I gave y'all an example in case you happen to see this somewhere else. All right, and usually as we go through the examples, we're going to highlight keywords. This example doesn't really have very many keywords, but as we go through, we'll always go through and underline the terms and everything that are going to be important. So let's write down what's known. We know our mass is 5 kilograms. Our pressure is 1.5 megapascal. And temperature is 440 degrees Celsius. And then specific volume is 0.2160. And that's cubic meters per kilogram. Now we want to find volume. So let's look at this and think about the equations that we've kind of had so far. Now if you remember, we talked about specific volume. We know specific volume is 1 over density, right? And what was density? Let's think about it. So density was mass per volume. So this is what we need right here is volume, right? So let's go ahead and combine this equation for density with this equation for specific volume. And let's see what we get. So now we've got that. Now let's get rid of this fraction on the bottom. That gives us that specific volume is equal to volume per mass. Now we want volume right here. We have mass, we have specific volume. We have everything we need now to find volume. We just need to reorganize that equation. So now we've got volume equals mass times specific volume. So let's plug in our values, make sure you keep the units. I know it's kind of a pain, but I promise you it pays off in the end. So we've got 5 kilograms times 0.2160 cubic meters per kilogram. Now let's cancel our units, make sure they work out. Those two cancel. So we're left with cubic meters, which is what we were wanting. So that looks good. Now let's multiply these numbers and we'll get our result. So we get 1.08 cubic meters. So that's your volume of water vapor. All right. So this is part A. Part B, we want to know the amount of water vapor present in moles. All right, so we haven't really talked about that, but I wanted to give you all this equation in case you need it in the future. So N, I'll tell you what that is in a second, is going to equal M, which is mass, over capital M. Now N is the number of kilomoles of a substance. All right, so that's what N is. And then little m is going to be your mass. That'll be in kilograms. And then that capital M is going to be molecular weight. Now the units for molecular weight are going to be kilograms per kilomole. Now if you get the book that I am recommending, the one that I use for this course, you can look in table A1 to find molecular weight. If you're not using the book that I have, your book has a table of molecular weights, you'll just have to find out where it is. Okay, so this is going to be a good equation to have in case you're ever asked about moles, things like that. Okay, so now let's put it all together and see what we get. So we want to find N. That'll give us the kilomoles, and then we'll work from there to get the number of just moles. So N is going to be our mass, which is 5 kilograms, over molecular weight. For water vapor, molecular weight is 18.02 kilogram per kilomole. So now let's look at our units. The kilograms, those go away. And we're left with kilomole. We don't want kilomole, we want regular moles. So we need to do the conversion for that. So 1,000 mole per kilomole will be the conversion we use. So this will cancel out the kilomole units, leaving us with just moles, which is what we wanted. So now I'll just do the math here. And you'll get 277.469 moles. Just like that. Okay? So now we know how many moles of water vapor we have present. And then C, we want to find the number of molecules. Now this is going to take you back to chemistry, probably. But here you're going to use Avogadro's number. Everybody's favorite number from chemistry. So remember, this is the number of molecules present in a mole. Okay. So the number is 6.022 times 10 to the 23. That's molecules per mole. So essentially, if we already have the number of moles, we want the number of molecules, we just need to multiply this number by Avogadro's number. So that'll be our last step. So take Avogadro's number, and then we'll multiply it by 277.469. That's mole. Okay, so the moles cancel, you're left with molecules, which is what we wanted. So that's 1.671 times 10 to the 26th, and that's molecules. Okay? So there's an example in case you're ever asked to find molecules or number of moles. That's how you would do it. Okay? So the next example will be our last one for this chapter. This one is going to be a piston cylinder assembly. It's sitting on this hot plate that can heat up. All right, so initially the hot plate is not plugged in, it's just cold, but then we're going to plug it in, it's going to start generating heat, and what's going to happen once we generate heat is this gas in here underneath the piston is going to start warming up. Now once the gas starts heating up, it's going to want to expand. So if it's wanting to expand, it's wanting to spread out. And the only place where it can go is to try to push this piston up so it can expand up in that cylinder. Okay, now what we want to find is what pressure in bar does the piston start rising. So what gas pressure is going to cause this piston to start moving up? That's what we're looking for. Okay, now notice initially the piston is resting on these little blocks here, so it's not moving downward. So the gas is going to heat up and then try to push that piston up. All right, so let's go over this one. First thing we're going to want to do is draw a free body diagram of the piston. All right, now this piston has a mass associated with it. It's 50 kilograms, so let's start with that one first. So that gives us a weight. So that's M times G. Now, if you look up here, this cylinder is open to the atmosphere. So that means there's going to be an atmospheric pressure. And it's telling us that that pressure is 1 bar. So that atmospheric pressure is going to be pushing down on the piston, like that. And then finally, this piston in here, it's got the gas in contact with it. So the gas is heating up, it wants to expand, so it's trying to push the piston up. So there's going to be a pressure going up due to the gas. All right. Now, normally when we draw a free body diagram, we don't have pressures. We usually have forces. So let's redraw that with forces. So weight going to stay the same because that's already a force. Now the other two, this atmospheric pressure, remember pressure is force per area. So we could rewrite that and say that that's a force due to the atmospheric pressure, and that's going to equal atmospheric pressure times area. Right? And then we can say the same thing down here for the gas. So the force due to the gas is going to be the gas pressure times area. And these areas are going to be the surface areas of the pistons. So all the area that's in contact with the gas or the atmospheric pressure. And that's given to us as 0.01. Right? Now think about what needs to happen in order for this piston to rise. So if you look at this diagram, we've got two forces pushing down, right? And only one pushing up. So that means in order for the piston to move up, that this force has to be bigger than the sum of these two forces. All right, so let's write that down. So for the piston to rise, force of the gas, it needs to overcome the weight plus the atmospheric force. So that means the force of the gas has to be at least equal to the weight plus the atmospheric force. All right, once it's equal to this, it can start moving up. So let's go ahead and rewrite this in terms of pressure because we want to solve for a pressure. So we'll have pressure of the gas times the area equals the weight plus the atmospheric pressure times area. And now we can start plugging our values in. This right here is what we're looking to solve for. So we're going to have the gas pressure times the area, which is 0.01 meters squared. That's going to equal 50 kilograms times 9.81 meters per second squared. So this is the mass times gravity. And then our atmospheric pressure, it told you it was 1 bar. We don't want units of bar in here because we've got meters. So let's go ahead and switch that over, and we're going to use 1.01325 times 10 to the 5th Newton per square meter. So this was in that list of the pressure values we talked about in the earlier video. And now let's multiply by the area. So 0.01 meters squared. All right, we'll write that right there. Okay, so now we have everything we need. We can solve for the gas pressure. All right. Oops. So our gas pressure that we're then going to get is going to be 150,375. It ends up being newtons per square meter. Okay. Now we want this in bar. Okay, so now we're going to go back to bar. So we're going to multiply by our conversion, which is 1 bar per 10 to the 5th Newton per square meter. So this cancels this, and what you get is 1.5 bar. All right. So that is your gas pressure that you're going to have in order to make that piston start moving up. All right, so it's got to be 1.5 bar. All right, guys. I will see you for the next video.